Now let us move to the next section where we will discuss all the user inputs that are required for setting up a Eulerian model. We will discuss all the user inputs in detail and also see the submodels within the Eulerian multiphase model. The first thing that you have to note is when we solve Eulerian multiphase model, all the equations are solved for all the different phases that are present. Momentum equation is solved for the continuous phase as well as all the dispersed phase also. So once we define phases in our problem, the next important task is to define how the phases interact with each other. The various physics involved in multiphase flow allows interaction between different phases in the form of either a drag force, lift force, collisions can also happen, there is a slip, heat exchange takes place between different phases, reactions can also take place between phases, there is entities like surface tension, etc. So when we define a multiphase problem, we have to define how these forces or how these phase interaction entities are going to be solved and how they are going to be defined. In order to capture interaction between different phases, modeling or capturing the drag force is very important. The most important force between different phases is the drag force. So when we are solving multiphase, we need to capture this drag force and model it. Drag force, as we all know, is given by Stokes' law. But the Stokes' law is theoretically defined for spheres in an irrotational flow. So in order to modify this Stokes' law for a generalized multiphase problem that we solve in Fluent, the drag force is modified by introducing a correction factor. As you can see here, this type of an correction factor is introduced. In this equation, F is a correction factor, and this correction factor is a function of particle Reynolds number. So this is how the drag forces are calculated in Fluent for any shape of dispersed phases. What we need to do is set up the drag coefficients or select different models that are available for drag coefficient within Fluent. Let us now discuss different settings and options available in the phase interaction panel. We will first discuss the input of drag coefficients. To define the phenomenon of drag between interacting phases, we have to set up drag coefficients. For this, we go to phases and then within the phases list at the bottom we click on interaction. Then the phase interaction panel pops up. The first tab in that is drag. We click on drag. It shows the two phases that we have defined, that is water and air. If more phases are present, we have to define interaction between pair of such phases. So always we have to define interaction between pair of phases. There are different ways or methods by which we can define drag. The first among them is Schiller-Norman. We use this configuration for spherical particles. The next configuration that we can use is Morse-Alexander, which is very close to Schiller-Norman, but it is generally not recommended. Also, a symmetric configuration is available. This is for very high secondary phase volume fraction. That is, if the secondary phase volume fraction goes to very high, closer to values like 1, we use this symmetric. We can also define drag by using user-defined configuration. If we already know some correlation for drag that we want to input ourselves, we can use the user-defined option and define a UDF to input the drag coefficient. So once we have defined drag between pairs of phases, we click on OK and we are done with defining the drag between different phases. The next phenomenon that we have to consider is virtual mass force. This captures relative acceleration between different phases. Now it is a tricky term and we have to know when to include this virtual mass force and when to neglect it. To define the virtual mass force, we go to phases and then click on interaction, and there is a tick option available called virtual mass. If we tick it, then virtual mass force is considered. If we do not tick it, then it is neglected. The main thing to understand here is criteria for including the virtual mass force. We include this when mesh size is less than length scale of acceleration. We can have an estimate of the acceleration of phases and the mesh size, and if we see that the mesh size is comparable or less than the length scale of acceleration, we include this virtual mass force. The next phenomenon is lift. Lift force captures shearing effect of the fluid onto the particle. This is the correlation for lift force. This is the relative velocity, and this is the lift coefficient. This is the lift force. We go to phases and then click on interaction. The second tab is for lift force. Again, similar to drag, it shows pairs of phases, and for that pair of phases we have to define lift force. We can either input a constant value or user defined correlation if we already know it. We have to define the lift coefficient. It is mostly included only for turbulent bubbly fluids. The next option in phase interaction panel is heat transfer. Phases can interact with each other by exchanging heat. The heat transfer mechanism needs to be modeled by giving various inputs in the heat transfer tab within the phase interaction panel. This heat transfer between different phases is referred to as interfacial heat transfer. There is a model available within Fluent which takes care of this interfacial heat transfer. We can either select that model or we can give our own model by using the user-defined function. This model is called as Ransmarshall and it is recommended for spherical particles. That is for modeling heat transfer when the dispersed space consists of spherical particles. This is functionally very similar to Schiller-Neumann model that we just discussed in the last few slides. To activate this model, we go into phases, then click on interaction, then the phase interaction panel pops up and we click on heat tab. Within this, we see a pair of phases that we have selected. One will be primary and the other will be secondary. And we are modeling the heat transfer between these two phases. If we have more phases in our model, then more such pairs will appear below. We have to select the model for heat transfer coefficient. That is, our input to Fluent will be heat transfer coefficient. We can select the Ransmarshall or we can give the user defined. Let us have a brief look at what the Ransmarshall model does. Now, we have to model the heat transfer, that is Q12. 1 refers to phase 1, 2 refers to the secondary phase. So in order to model this heat transfer between two phases, that is Q12, that is heat exchange between two, we know that it can be modeled as heat transfer coefficient into the temperature difference. Temperature difference is already part of the solution, that is Fluent already solves for temperature for both the phases. So this will be taken care by the solver. All we need to give is the heat transfer coefficient H12. Now the Ransmarshall uses this configuration for heat transfer coefficient. This is the Nusselt's number, and this Nusselt's number is calculated based on Reynolds number and Prandtl number. So this is how the calculations are done. This is the diameter of the dispersed phase, that is the phase 2, and Fluent uses this configuration to calculate the Nusselt's number. From that, it calculates the heat transfer coefficient H12, and that is used within the Ransmarshall model. Now we will see how to model turbulence when we are using the Eulerian multiphase model. We have to start with selecting a single phase turbulence model from the viscous model panel, which is here. That is, we select a main turbulence model for modeling single phase. The options available are K epsilon, K omega or Reynolds stress. Then we select parameters for individual models. Like for K epsilon, we can select standard, RNG or realizable, and also various other options like RNG options, near wall treatment, etc. So we select all these models, this turbulence model, initially as if we are modeling a single phase problem, and we select the model for only single phase. Next, we select the desired multiphase model. That is, we go here into turbulence multiphase model section. We can select mixture, disperse or per phase. 3 options are available. Once we have selected for single phase, then we select the multiphase turbulence model. As you can see, we have mixture here, we have dispersed or per phase. Let us see what these individual models mean and how do we select depending upon which problem we solve. The mixture model. The mixture model as seen here can be selected from the turbulence multiphase model section within the viscous model panel. This is the default, that is, if we don't select any turbulence model for multiphase, this is the default that Fluent uses. In this model, mixture properties are used for all turbulence related parameters. That is, when solving turbulence equations, the properties, that is material properties and various other physical and chemical properties that are used as mixture phases. They are not used for individual phases, but they are used as a mixture. Then the turbulence model solves for mixture phase. That is, for individual phase, turbulence is not solved. Turbulence is only solved for mixture phase. That is, mixture of the different phases that we are going to use. So turbulence is not solved in detail for each individual phase. So this is the mixture model. Next is the disperse model, and we can select it here. The disperse model is applicable when there is a clearly one primary continuous phase. That means we can distinctly say that this one particular phase within different phases that we have selected is the primary phase. That is, it is present predominantly, whereas rest of all the phases are dispersed and are dilute. So compared to all other phases, the primary phase has the most presence and it is the continuous phase. And then only this model is applicable. This model includes the effect of particles on single phase turbulence. So it includes the effect that particle will have on the single phase turbulence. So turbulence is modeled in much detail than the mixture model, but here the criteria is that a single phase should be the continuous phase, that is, it should be predominantly present while the rest of all the phases should be dilute and secondary. Third is the per phase model. Here we model turbulence for each phase, that is, turbulence equations are solved for all the phases that are present. This is appropriate only when there is predominant turbulent transfer between phases. There is a highly extensive calculations are involved, so it is expensive in terms of computation, but it solves turbulence for all the phases and it is a highly detailed model. Now we will see how to include boiling model when we are using the Eulerian model. If we have to consider boiling phenomenon in the problem that we are solving, we need to activate the boiling model within Fluent. For this, we go to Model, Multiphase and Edit. That is, this panel will pop up. Here we say the Eulerian model. Then we enable the boiling model under the Eulerian parameters. When we tick this, then the boiling model will be included and we can model the boiling phenomenon in our problem. After selecting this, we select the RPI boiling model or non-equilibrium model. These are the two options that are available while using boiling model. We also set the total number of phases. We can include as many phases that are present in our problem. Now this is how we activate the boiling model. There are various other details that we have to consider while modeling boiling within Fluent. We will study the entire modeling process of boiling in a different section in the coming courses. For the time being, what we will see is just how to activate the boiling model and how to select the Eulerian parameters for activating the boiling model. Another specialized submodel within Eulerian model is the immiscible fluid model. We have to use this when we are modeling immiscible fluids. We go to Model, Multiphase and Edit. Then again this panel pops up and we select the Eulerian model. We enable the immiscible fluid model under the Eulerian parameters. If we take this, we can model the immiscible fluids. We set the total number of phases in this section. Point that is to be noted is that we cannot use this model with the dense discrete phase model. So this is a specialized model for modeling immiscible fluids. Let us now see the next submodel within the Eulerian model, which is called as dense DPM, that is dense discrete phase model. This model allows us to track particles using DPM as secondary phase in an Eulerian simulation. Now, as you may remember, if we are using the Lagrangian equations for discrete phase within the DPM model, it has a limitation that the discrete phase volume fraction should be low. Then only we can use the DPM model. In case the discrete phase volume fraction is high, but still we want to track particles, then what should we do? In such cases, we should use the Eulerian simulation, there is an Eulerian model, and use the dense DPM model so that we can track the discrete phase also, as well as we are not having problem with the limitation of the DPM model. So this is meant for such condition where the discrete phase volume fraction is high, but still we want to track the discrete phase. For using this model, we go to Model, Multi-Phase and Edit. Then the multi-phase model pops up. We select Eulerian. We click on the dense discrete phase model within the Eulerian parameters and activate the dense discrete phase model. We also enter the number of discrete phases here. We go to Model, Multi-Phase and Edit. The multi-phase model panel pops up. Then we enable the dense disk DPM model under the Eulerian parameters. That is here, we click on this, so the dense discrete phase model gets activated. First we set the number of Eulerian phases. We set the number of discrete phases and the Eulerian phases. That is, we input here and the number of discrete phases we enter here. In case of dense discrete phase model, volume fraction at drag are considered like an Eulerian phase. So only the particles are tracked using the Lagrangian tracking, whereas rest of the equations are solved using the Eulerian method. Now when we use the dense DPM model, the discrete phase model, that is the DPM model, automatically gets activated. We have to input all the settings of the discrete phase model in order to define the discrete phase injections, the discrete phase particle parameters, etc. So we have to do all those settings after we activate the dense DPM model. For this, we go to Problem Setup, Phase, Discrete Phase and then to Edit. That is, we enter into Problem Setup, Phases. The phase list appears. Here the second phase now is not secondary but it is a discrete phase as we have defined it. Then we click on Edit. After that, this discrete phase panel pops up. Here we enable the volume fraction approaching continuous flow limit, that is, we click on this. Then we specify a transition factor here. Once we have activated the dense DPM model, we need to define properties of discrete phase and of injection similar to the way we define for DPM model. We need to define how the injections of the discrete phase come into the domain and what are their initial conditions. For this, we need to define injections for discrete phase. To define injections, we go to Define and then Injections. We click on Define, which is here, and then a drop-down list comes up. Then we click on Injections in the drop-down list. Then the injection panel pops up. Here, currently there is no injection defined, so we click on Create. This will create new injections and take us to the Injection Properties panel. Here we set the injection properties. We define the injection name, the injection type, as well as the material used for the discrete phase. We also define rest of the initial condition for injections like X, Y, Z position, injection velocities, etc. In short, we input all the injection parameters and define a new injection. This injection will be treated as an injection for the discrete phase for the dense DPM model. I would like to say thank you for viewing this particular lecture. If you have any doubts, you can always contact us. So thank you for viewing this lecture and see you in the next lecture.